In 1977, a radio telescope detected a signal so unusual that an astronomer circled it and wrote "Wow" on the printout. Jerry R. Ehman sat at his desk at Ohio State University's Radio Observatory, reviewing the latest data printouts from the Big Ear telescope. The computer paper showed columns of numbers and letters representing radio signal intensities. On August 15, 1977, one particular sequence caught his eye: 6EQUJ5. This sequence wasn't random noise. It represented a signal that grew in strength for 36 seconds, peaked, then faded over the next 36 seconds, a total of 72 seconds that would become legendary in astronomy. Ehman took his red pen and circled the unusual sequence. In the margin he wrote a single word: "Wow." That spontaneous reaction gave the signal its famous name and marked a pivotal moment in the search for extraterrestrial intelligence. Each character in the sequence represented a specific signal strength, with numbers 1 to 9 showing increasing intensity, and letters A to Z indicating even stronger signals. The peak at U meant the signal reached 30 times the background noise level, an unprecedented observation. The signal's frequency measured 1,420.4056 MHz, known as the hydrogen line or the universal beacon. Hydrogen, the most common element in the universe, emits radiation at this frequency, making it a logical choice for interstellar communication. The signal's bandwidth was less than 10 kHz, extremely narrow by cosmic standards, as natural sources like pulsars or quasars emit much broader frequencies. Big Ear's design made terrestrial interference unlikely. The telescope used two feed horns that alternately scanned the sky. A signal from Earth would appear in both horns simultaneously, but the WOW signal only appeared in one. The timing matched how long a point in space would take to pass through the telescope's fixed beam due to Earth's rotation. Researchers traced the signal's origin to the constellation Sagittarius, near the Chi Sagittarii star group. The signal's intensity curve, rising and falling like the notes of a symphony, matched what astronomers would expect from a distant fixed source. Its hydrogen line frequency suggested intentional targeting, while the narrow bandwidth hinted at an artificial origin. Yet the signal never repeated. No known astronomical object matched its properties, and the transmitter power required would have been far beyond 1970s human technology. The odds of such a signal occurring randomly were vanishingly small. Let's examine the case for the WOW signal being an intentional extraterrestrial transmission. The hydrogen line frequency provides the strongest initial evidence. At 1,420 MHz, this matches the natural emission frequency of hydrogen atoms in space, a universal constant that any advanced civilization might recognize as the cosmic language everyone could understand. Could this be a deliberate call from the stars? The signal's narrow bandwidth strengthens the case. Natural cosmic radio sources like pulsars typically emit across millions of hertz, creating broad, noisy signals. In contrast, the WOW signal measured less than 10 kHz wide, a precision that aligns with what scientists predict for an engineered transmission. Concentrating power into such a specific frequency maximizes detectability, a hallmark of intentional design. Adding to the intrigue, the signal appeared in a protected radio band. International agreements reserve the 1,420 MHz frequency for astronomical research, making Earth-based interference highly unlikely. The signal's strength also suggests an extraordinary source. Calculations indicate it would require a transmitter with at least 2.2 gigawatts of effective radiated power if it originated from nearby stars, far beyond human capabilities in the 1970s and even challenging by today's standards. The timing and duration offer further clues. The 72-second signal matches the time it would take a fixed point in space to pass through the Big Ear telescope's beam due to Earth's rotation. This consistency suggests the source was stationary in space. The signal's intensity curve, rising and falling smoothly, fits this scenario perfectly, further ruling out moving or transient sources. No known natural phenomenon combines all these characteristics. While some cosmic events can emit near the hydrogen line frequency, none replicate the WOW signal's precise combination of narrow bandwidth, clean intensity curve, and one-time appearance. Natural sources typically repeat or leave observable aftereffects, which the WOW signal lacks. Before concluding the signal came from aliens, we need to consider how natural phenomena might mimic artificial transmissions. Throughout history, astronomers have often mistaken natural events for something extraordinary. For example, pulsars, rapidly spinning neutron stars, were initially thought to be signals from extraterrestrial civilizations when first discovered in 1967. This serves as a reminder that nature can produce phenomena that seem deceptively intentional. One possible explanation for the WOW signal involves hydrogen clouds in space. These vast regions of interstellar gas naturally emit at 1,420 MHz, the same frequency as the WOW signal. Under rare conditions, their emissions might align to create a stronger, temporary signal. Similarly, interstellar plasma, the ionized gas between stars, can act like a lens, focusing radio waves and amplifying weaker emissions. While these processes could theoretically produce a signal resembling the WOW detection, neither fully accounts for its intensity or narrowband nature. The conditions required remain speculative and unobserved at this frequency. A more specific natural explanation comes from a 2022 study involving magnetars, neutron stars with extremely powerful magnetic fields. These stars occasionally emit intense flares, and if such a flare passed through a hydrogen cloud, it could theoretically produce a narrowband signal at 1,420 MHz. Instrumental issues also warrant consideration. The Big Ear telescope, while advanced for its time, wasn't immune to technical glitches. Jason Wright notes that one-off signals often trace back to equipment anomalies. Without repeat detections, it's difficult to rule out the possibility that the signal was an artifact of the telescope's systems rather than a cosmic event. Finally, terrestrial interference remains a plausible explanation. Yvette Sendez argues that human-made signals, such as transmissions bouncing off space debris or atmospheric layers, could explain the WOW signal's characteristics. Although the 1,420 MHz band was protected, enforcement wasn't perfect, and brief leaks into this frequency could have occurred. Why did the WOW signal vanish? That single 72-second burst in 1977 remains one of the greatest mysteries in radio astronomy. Despite over 100 targeted searches of the same patch of sky near the Chi Sagittarii star group, using increasingly advanced equipment, nothing like it has ever been detected again. This absence has left scientists grappling with more questions than answers. The Allen Telescope Array, designed specifically for SETI research, dedicated thousands of observation hours to the WOW signal's suspected origin. Its advanced capabilities should have easily picked up any repeating transmission, yet it found nothing. Similarly, the Breakthrough Listen project, which has scanned millions of stars, has detected numerous intriguing signals, but none that replicate the WOW signal's unique combination of frequency, duration, and intensity. Part of the challenge lies in the limitations of the Big Ear telescope, which detected the signal. While groundbreaking for its time, its directional precision was crude by today's standards. The telescope's beam covered an area about twice as wide as the full moon, making it impossible to pinpoint the exact source. Modern instruments can localize signals to fractions of a degree, but without knowing precisely where to look, the search becomes like finding a needle in a galactic haystack. Some researchers propose the original detection might have been an extremely rare statistical fluke. Radio telescopes process vast amounts of data, and occasionally random noise can align to mimic a meaningful signal. However, the odds of noise perfectly matching the hydrogen line frequency while also displaying the correct intensity curve seem astronomically low. The signal's characteristics were too precise to dismiss as mere chance. Today's astronomers tackle the WOW signal mystery with tools that represent a monumental leap from what Ehman had in 1977. The Breakthrough Listen project, for instance, scans the skies with algorithms capable of processing millions of radio channels simultaneously. These machine learning systems, like digital bloodhounds, are trained on known signal types to sniff out anomalies. When applied to archival data, they've uncovered faint signals sharing some traits with the original WOW detection, though none match its full profile. This suggests the 1977 event might be the strongest example of a rare but recurring phenomenon. The Very Large Array in New Mexico offers another cutting-edge advantage. Its 27 movable dishes form a virtual telescope nearly 22 miles across, enabling precision measurements far beyond the Big Ear telescope's capabilities. If a WOW-like signal reappears, the VLA could pinpoint its origin within arcseconds compared to the several degrees of uncertainty in 1977. New analysis techniques explore how natural processes might mimic artificial signals. For example, a magnetar flare intersecting with a hydrogen cloud could produce narrowband emissions at 1,420 MHz. Another model suggests comets passing through interstellar medium might create temporary radio bursts. While each explanation has flaws, they show how ordinary cosmic events could combine to produce extraordinary signals. The WOW detection might have been a perfect storm of natural phenomena rather than a technological broadcast. The 2022 Magnetar hypothesis offers a breakthrough natural explanation for the WOW signal, surpassing earlier theories that struggled to account for its unique characteristics. Astronomer Abel Mendez and his team proposed that a flare from a magnetar, an ultra-dense neutron star with an extraordinarily powerful magnetic field, interacting with a hydrogen cloud could produce the distinctive signal. This process unfolds like a cosmic laser show. The hydrogen cloud emits at its characteristic frequency, while the magnetar flare provides the energy boost needed to amplify the signal across interstellar distances. The result is akin to a naturally occurring hydrogen maser, a focused radio emission that appears artificially precise. This mechanism elegantly explains the signal's narrow bandwidth, its precise frequency alignment with neutral hydrogen, and its unusual intensity, which initially suggested an artificial origin. The hypothesis also clarifies why the signal never repeated. Such alignments between magnetar flares and hydrogen clouds are extraordinarily rare. The geometry required, a magnetar flare intersecting a hydrogen cloud along our line of sight, would last only briefly before the object's motions disrupted the alignment. Mendez's team calculated that such events might occur naturally about once per century in our galaxy. This rarity explains why no similar signals have been detected since 1977, while highlighting the Big Ear telescope's extraordinary luck in capturing one. As Mendez noted, this is a rare but plausible event, grounded in known astrophysics. The WOW signal remains astronomy's most tantalizing unsolved mystery, a reminder of how much we have yet to uncover. Whether it was a natural phenomenon or something more, its true impact lies in how it propelled radio astronomy forward. It inspired advancements in telescope design, data analysis, and SETI research, reshaping how we explore the cosmos. As astronomer Robert Gray described, it's a tug on the cosmic fishing line that keeps scientists searching. What does this tell us about our place in the universe? Perhaps the greatest discovery is the balance between what we know and the mysteries that remain.